start, I'll start with an apology. Class today will not be properly recorded because the microphone is locked in Nili's room and has no access. So I apologize. So we are interested in the pattern of spiking activity in the cortex. We were horrified to learn on Sunday that we repeat the experiment and we don't get the same results. The pattern of activity differs between trials. One potential answer was biological noise, whatever it means, but certainly we are not satisfied with such an answer, because first we would like to know what this biological noise is and how can we reduce it, and how come that by doing more careful experiments we don't get more careful, the results don't seem to be better. The reproducibility of the experiment doesn't seem to depend on our quality as experimentalists. And this tells us that maybe there's something else going on. And then we started with a detour intended to provide us with tools to characterize the neural activity as a stochastic process. And we introduced the terms point process, and we introduced and we discussed what a Poisson process is. And the Poisson process is basically a stochastic process such as the probability of an event at any point in time. A homogeneous Poisson process is a stochastic process such as the probability of an event at any point in time is equal, and we're interested in the timing of these events. And we ended class with relating Poisson process to Poisson distribution. So I'm sure that all of you encountered Poisson distribution somewhere along the way during your studies, and what we did was to relate Poisson process to Poisson distribution. Any questions about that? So before leaving Poisson, before going back to that, before going back to the brain and showing you that Poisson process is a reasonable description of activity in the cortex, I'd like to tell you a little bit about some more properties of Poisson process, because these will be measures that we will consider when talking about activity of cortical neurons. So one question that we will consider is about the distribution of inter-event interval in a Poisson process. The distribution of I will already call it inter-spike interval. So we'll think about action potential, and the question will be, assuming that spikes are described by a homogeneous Poisson process, what will be the distribution of the intervals between the spikes or inter-spike intervals? And it's rather straightforward to prove that this distribution is exponential. Can I skip it? You already know. All of you know it, or okay. So I'm going to prove that the distribution of inter-spike intervals is exponential. So the way to prove it is the following. So what's the probability that an interval, let's call it tk, let's call it t, that an interval t will be between t and t plus delta t. So we have two. These are the times of our spikes, and this is one of the inter-spike intervals, one of these events. And the question: what's the probability that this event will be between time t and time t plus delta t? This is the question. So this is equal to the probability that there was no event at time t prime that is smaller than time t. So the one requirement that there was no event prior to time t, right? And that there was an event, there was a spike between somewhere in the interval between t and t plus delta t. Right? So in order for the interspike interval to be between t and t plus delta t, there should have been no event up to time t, and there was an event between t and t plus delta t. Okay. So what's the probability? So what's the probability of no event at all times t prime that is smaller than t? How are we going to compute it? So what does it mean that there was no event up to time t? How are we going to compute it? So we have a Poisson process. I didn't characterize its rate, but the rate is lambda. So I started class today by relating Poisson process to a Poisson distribution. So we already know what's the probability of having 0 events in an interval. What is this probability? This can be computed from the Poisson distribution. Which is, what's the answer? Going back to your notes. E to the minus lambda t. This is the probability of having 0 events in an interval of length t, when the rate of the process is lambda. If you don't remember the formula, the way to do it is just divide this interval t into a small interval delta t's, the probability of having no event in each of these intervals is 1 minus lambda delta t. And then take the limit, take the product of all these, so there's no event at time delta t, first delta t, second delta t, third delta t, and so on, and then take the, so we have a product of 1 minus lambda delta t of t over t delta t, such product, and then we take the delta t to 0 when we get the exponent. That's the way to compute it. So the probability of no event at an interval smaller than t is e to the minus lambda t. And what's the probability of having an event? What's the probability of an event at interval t to t plus delta t? It's true that it's 1 minus the probability that there will not be such an event, or it's just equal to lambda delta t. So the probability that the interspike interval will be between t and t plus delta t is just the product of these two terms, because they are independent. In Poisson process, any two events are independent. This is just equal to lambda e to the minus lambda t times delta t. So the probability distribution, PDF, of t is just equal to lambda e to the minus lambda t. So the probability distribution function for an interval t is just lambda e to the minus lambda t. So a signature of a Poisson process would be an exponential distribution of inter-event interval. Or put differently, if you observe in nature something that is exponentially distributed, that the intervals are exponentially distributed, then there's a good reason to suspect that we're talking about a Poisson process. So what's the average t? What's the average interval in a Poisson process? This is just the integral from 0 to infinity of t times probability of t dt, which is equal to the integral from 0 to infinity of t lambda e to the minus lambda t dt, which is equal to 1 over lambda. This is useful to know that the average interval is just over 1 over the rate, this is something that we could have suspected without doing the math, because this is the only time scale in the problem is 1 over lambda. Another useful quantity is known as coefficient of variation. Coefficient of variation, also known as CV, which is defined as the square root of the average fluctuations divided by the mean. So this is a measure of the, you can think about it as something like noise to the signal, or to what extent the these interspike intervals fluctuate relative to the mean. So let's assume that that we have a process that is completely regular. What will be the CV in a process that is completely regular? 0, because the variance is 0. So this ratio would be equal to 0. So this quantity, fluctuations divided by the mean, are a measure of the regularity of our process. So if we have a process that we want to quantify how regular it is, this is a useful measure that will give us 0 for processes that are completely regular. Delta t is defined as t minus average t. So basically what you do, you take all the intervals, you subtract the mean, you square, and you average. So this is the variance in these intervals. So how are we going to compute this? What's delta t squared? Delta t squared average is just equal to t squared average minus average of t squared, as you all know. So to compute t squared average, all we need to do is compute this integral, but with t squared. To do integration by parts, and I leave it to you as an exercise to show that the CV of a Poisson process is equal to 1. So again, if you have a process, you look at the intervals, you compute the CV. If you find that the CV is 1, it's an indication that the process is a Poisson process. Of course, it's not a proof, but it's an indication. And this is easier than computing the distribution of interspike intervals, because in order to compute to properly compute a distribution, you need many more numbers than to compute a single number, a CV. Can CV be larger than 1? Yeah, sure, why not? Can you imagine a process that will give you a CV that is larger than 1? What do you mean by random? This is random. Poisson is random. So this is a quantity that is often used to characterize neural activity. So it can be larger than 1, can be smaller than 1, can be equal to 0. This is an example. A completely regular process will give you CV of 0. But can it be larger than 1? The answer is yes, but let's think about an example. I'm sorry? How will the spike train look like? Give me an example of spike train that will give you a CV that is larger than 1. That's sometimes they're very close to each other, and sometimes very burst. So a bursty, exactly, a bursty, something that looks like this. This spike train will have a CV that is larger than 1, and indeed you see things like that in the cerebellum, in Purkinje cells, at least in anesthetized animals. I'm not sure about awake. It's more complicated in awake, but in at least in some animals, at least in guinea pigs and mice and rats, you see these in anesthetized animals. And you also see it in awake in cats, but not sure about other animals. Okay, so we have a characterization of the interspike interval. We have a measure of regularity, which is CV, coefficient of variation. Before showing you some examples of Poisson processes, it's often useful to simulate Poisson processes. So in order to simulate a Poisson process, basically you need to generate events or spikes that have these properties of the Poisson process. So how are we going to do it? What are the ways? So there are various ways of simulating Poisson processes. So how are you going to do it? Let's say you have an exercise. You need to generate a Poisson spike train for one reason or another. How would you do that? So your task is to generate a Poisson process with a rate lambda and interval t, capital T. Now, this is not the interspike interval, but this large T is the duration of the process. So how are we going to do it? Okay. So this is one way. This is one way. We will talk about it in a second. And the question is how to generate exponential.
This is the reverse of the CDF.
Reverse CDF, exactly. This is one way. So let's start with a naive way. So remember, in the Poisson process, the probability of an event, clearly your way is better, but I'll start with a simpler, more trivial way. So we know that in the Poisson process, all events are independent from each other and have some probability. So one way of doing it is dividing our interval t to small bins of size delta t and draw an event in each of these with a probability lambda delta t. So the probability of an event is lambda delta t. The probability that there will not be an event is 1 minus lambda delta t. And this is a way of generating a Poisson process. The problem in using this approach is that the accuracy of the process will depend on delta t. We want to take the limit of delta t to be equal to 0. In the smaller delta t, the larger the number of Bernoulli processes that we need to simulate. Now, if lambda, so that's a limitation. This is a direct approach, but it's clearly not optimal. There's another way. There's another way of doing it, and this is the following. So this is method number 1. This is method number 1. Your method will be method number 3. The second method is to use the fact that we know what is the distribution of number of events. So we know that the total number of events, so the total number of events, I'll denote it by n, is Poisson distributed with a mean which is lambda t. So another way of simulating a Poisson process is first to draw the number of events from a Poisson distribution, and then randomly allocate these events along the line from 0 to t. So basically generate, after drawing n events, we will draw let's call this T, tittle. We will draw n numbers from between 0 and 1, and then multiply them by the total interval. So rather than, in this case, we had to draw to simulate a Bernoulli process in T over delta T intervals. Now all we need to do is do one time draw a number from a Poisson distribution, and then draw a random number from 0 to 1 multiplied by T for the scale, and repeat this n times. So that's the second way, which is computationally less expensive and clearly more accurate. So this is the second way of doing it. I'm not. So the question is to clarify this second method, right? So so we know. So there are two parts here. One is to decide how many events there will be here, and this is clear. Okay. So now the timing of each of these events. Now we know that the events are independent of each other. And in a homogeneous Poisson process, they can occur at equal probability at any point in time. So basically, we take all these different events and randomly place them between 0 and T. We're not talking about, these are not the intervals, these are the timing of the events themselves. Is it clear? You seem unhappy. You seem unhappy. Okay. So the third method is the method that you propose, is to use the fact that the distribution of inter-event interval is exponential. So if we draw intervals from an exponential distribution, we can just sum them, consider the cumulative of these exponential of these inter-event intervals that we drew from the exponential distribution. We can do it in order to generate the times of the events. So all three methods will result in are in fact equal. Of course, considering this method in the limit of delta t going to 0. I wonder whether I should go into the details of how to generate an exponential distribution from a uniform distribution. Is it something that you feel comfortable about? Or, yeah, let's just leave it. We will have it in the notes, or I don't know, in an exam or something. So now I would like to show you some examples of Poisson distributions and to talk about, say a few words about the brain. So I'm going to show you, hopefully I'm going to show you my hopes will come true. I'm going to show you several distributions of inter-event intervals from things that I studied over the years. Yeah, this would be the first one. Anyone wants to take a guess what it is? So I'm going to show you in the distribution of inter-event interval. Hopefully it will become less dark, but still you can see it. So the bars are the data, and this is just an exponential fit. Sorry? This would be, I'm sorry? Firing of bursty activity. So two things. The answer is no, but it's important to understand why. So first, bursty activity will, in general, will not give you exponential distribution of inter-event interval. So going back to the example that we discussed previously, if you have something that looks like this, then if you look at the distribution, so the distribution will be such that you have many small and a few very large. So something like this, I don't know. Whether there will be another peak here or not will depend on the details, because we don't have many of these. But you don't expect to see an exponential distribution when activity is bursty. This is one thing. And second, the time scale here is hours. Okay? So it can't be very fast. So, of course, you cannot guess, which is just, I mean, there's no way in which you can guess. Just to wake you up, this is the delivery interval in a hospital. Inter-delivery interval. So you have women coming, they give birth, okay, and you register the time of the event. Okay. And I'm looking at these intervals, okay? Inter-delivery interval in a hospital. Now note that to a first approximation, women are independent of each other in their timing of giving birth. Okay, so if I go to a hospital and I give birth, which is unlikely, but just for the sake of discussion, and you go, there's no reason why we will go together. We will give birth together. So there's no reason. No. So these are events that are independent of each other. The timing of these events are independent of each other, and as a result, the inter-event interval is the events themselves are approximately Poisson process, and the distribution of inter-event interval is approximately exponential. And there are various reasons why you should care about it. Well, one, for the sake of this class, is we are learning about Poisson processes. This is just, I think, a nice example that illustrates this idea. But second, let's say that you are managing a hospital. You will be very interested in the distribution of events and the fluctuations, because you don't only care about you want to be ready to events in which many women come at the same time. So you care very much about the fluctuation. What's the probability that within 2 hours, 17 women will be admitted and some of them will be left in the corridor? So that's why these things are important. Now, it's only approximately exponential. The reason that it's only approximately exponential is that if you look carefully at the data, there are hours that are more prone to deliveries, like between midnight and 6 a.m. women are reluctant to give birth, which is understandable. And also there are small fluctuations between the days. At least in Jerusalem, women are reluctant to come on Saturday, so there are fewer deliveries on Saturdays. You can also, I think, understand why. There are also some fluctuations around the year. I don't know, if you're planning your pregnancy, if you're a teacher planning your pregnancy, you can imagine that there will be dates that are better than others, thinking about vacations. But these are small fluctuations from a homogeneous Poisson process. And as a result, the distribution of events of inter-event interval is approximately exponential. I strongly suspect that these two events are issues related with writing, so they didn't register correctly in the hospital records. These two outliers. This is an issue of the records. Another example, which is perhaps more amusing, at some point in my life I was studying basketball, okay? In basketball, where the goal is to put the ball in the basket, that's why it's called basketball, and you can do it from far away, and then you get 3 points, and you can do it from nearby, and then you get 2 points. 3 is better than 2, but it's more difficult. Basically, these are the rules of the game. And I was thinking about basketball in the framework of reinforcement learning, but this is not important for the purpose of our discussion now. If you look at an individual player, you can look at the sequence of actions. So this was a 3-point attempt, and then he made a 2-point attempt, and a 2-point attempt, and a 3-point attempt, and so on and so forth. So there's a sequence of events of a basketball player, and we can take this sequence and consider the inter-event intervals. So for example, this would be for Kobe Bryant in one season. This would be the inter-3-point attempt interval. So we can record the time between different attempts and look at the distribution. And the distribution is approximately exponential. And we can do the same trick for the inter-2 interval, and it is also approximately exponential. Now, it cannot be exactly exponential. Why can't it be exactly exponential? Let's think about time 0. You cannot throw 2 balls at exactly the same time or at an interval of or 1 second apart, right? Because there's only 1 ball in the game. You cannot do it. Also, the long time, the game ends at some point, right? So we don't expect to see intervals that are longer than the length of the game. But I think that you would agree that to a first approximation, an exponential fit is not too. It's not such a bad. It's not such a bad approximation.
For real?
Well, this is a data. This is a data. But now that's very good, because now you are saying, okay, I learned something. I learned that Poisson processes are independent events. Independent events yield an exponential distribution of events. So if we see this leads us to think that these events are independent, right? This would be the logic. Are these events independent? You're not sure.
I don't think so.
Well, okay, so how come? So I'm going to argue that in the time scale of these events, in fact, they are approximately independent. And I will tell you why. If you look at the very short time scales, like, I don't know, seconds apart, clearly events are dependent. If I'm making an attempt, then clearly I will not be able to make an attempt a millisecond later. So clearly on a time scale of seconds, events are dependent. But the inter-event interval in basketball, I mean, you see the numbers, are on the order of hundreds of seconds. So if you look at the game, a player passes the ball on a time scale of seconds. The ball passes from one team to the other in time scales of tens of seconds. So if you succeed or you don't, if you score, then the second team gets the ball. So there are correlations, but this is on the time scale of tens of seconds. So the events that we're interested in or the inter-event intervals are on time scales that are longer than the characteristic time of the game. So within hundreds of seconds, you have sufficient mixing in the game such that these events are approximately independent. This is my interpretation of these results. So it's true that on short time scales the events are dependent, but on very long time scale, hundreds of seconds, these events become independent. And that's why we get an exponential distribution. This is my interpretation. Now if you look at the deliveries, there are also on very short time scales there will be dependencies, because you have a limited number of stuff, and so even the registration of the event itself, there are temporal dependencies, but they are much shorter than the characteristic time of these events. You had a question.
Yeah, I just wanted to ask, why do you separate between the 3 points and the 2 points? It's just not...
Why do I separate the 2 point to the 3 point? The reason is laziness, and allow me to elaborate. The goal of the study was to say something about learning, and it turned out that the separation of 2 points and 3 points is something that is crucial cognitively and manifests in the learning pattern of these players. Now, when preparing class, I took the figures from the paper and did not bother to put everything together. That's right. Okay, these are 2 examples which are amusing, but perhaps not relevant. What is more relevant are experiments. So this is one example of an experiment in which they used the moving dots paradigm, which is very popular, or at least used to be very popular in monkey research, also to some extent in humans when studying decision making. So the idea is the following. The subject is presented with dots that move on the screen and has to indicate whether they move in one direction or the other. For example, all dots can be moved in one condition, which is known as 100% correlation, all move in one direction. It will be either, let's say, up or down, and the subject has to indicate whether they move up or down. To make the task more difficult, there is a condition in which a fraction, let's say in this case 50%, move up, and the rest move randomly. So it's more difficult to observe the upwards motion. And in this condition, the uncorrelated condition, they just move randomly. And typically what people do, they use different values of correlation and compute and plot a psychometric curve and do things with it. I'm going to show data from this condition, just from those trials in which there were no correlation, but this we will do immediately after the break. Okay. למעשה מה שאת אומרת קורה, זה לא צריך שזה יקרה 3 פעמים. מספיק שזה יקרה פעם אחת, זה אפקט שהוא אפקט משמעותי. נכון, ולמעשה זה תהליך פואסון לא הומוגני, אבל שאלה של של תיקון שקורה מעבר לתהליך הפואסון ההומוגני. אם זה התהליך פואסון הומוגני, הייתי מקבלת משהו שהוא אקספוננציאלי בדיוק ויפה. מה שאת מקבלת זה יותר מורכב, אבל הקירוב הראשון שלו זה משהו שהוא אקספוננציאלי. משהו בתהליכים שאת מדברת עליהם ישבו על, אבל ההבנה של הקשר בין פואסון ואקספוננט כבר מספר לך משהו, לא סתם ציינו את זה, ציפינו שזה יהיה אקספוננציאלי. שוב, מתוך הבנה של מערכת תהליכים פואסוניים, מתוך הבנה של טיים סקייל של משחק.
אני כן הייתי לא מוכנה, כי אני לא הייתי משהו בדרך השנייה של מערכת הסימולציה. מה ההבדל בין מה שעשית לבין להגיד, אני פשוט אביא לך מספר, לא אכפת לי מאיפה הגרלת אותו, בפואסון או משהו אחר, ועכשיו תעשה בדיוק את אותו תהליך.
כי המספר שאת מביאה לי יכול להיות לא קשור לשום דבר.
אבל זה לא אומר שנגיד איפה הפואסון משפיע על זה שכשאתה אחרי שהבאת לי את המספר ואני עכשיו תוגמת מספרים מההתפלגות האחידה ומציבה אותם פה, שאלה יהיו אקספוננציאליים.
כי את לוקחת התפלגות אחידה של אירועים על אינטרוול, התפלגות הזמנים שלהם תהיה אקספוננציאלית.
כי אם אני לוקחת...
זה מה שעשינו עכשיו, לא עכשיו, בתחילת השיעור.
שמה? זו טענה כללית יותר שאומרת, לא אכפת לי איך אני לוקחת מספר שלם ועכשיו בוחרת למקם אותו בצורה רנדומלית על הקו, אז ההפרשים האלה יהיו אקספוננציאליים תמיד.
אם את לוקחת, זה כמעט נכון, עד כדי המספר שאת בוחרת.
אם הייתי דוגמת את ה-n, לא מההתפלגות הפואסון, אפילו הייתי דוגמת אותו בינומי. אז זה לא היה נכון? זה לא היה אקספוננציאלי? כאן?
כן. כי אנחנו רואים כאן, שוב, ההתפלגות האקספוננציאלית היא נכונה רק על אינטרוול שהוא אינסופי גדול. לא נכון באינטרוול אינסופי. by construction, לא יכולה לקבל התפלגות אקספוננציאלית על אינטרוול שהוא אינסופי.
ההתפלגות האקספוננציאלית לא הייתה אינסופי, רק על אלה.
לקבל אינטרוול, סיכוי לקבל אינטרוול שיותר ארוך מ-T הוא 0.
נכון.
ההתפלגות האמפירית שתקבלי, אינטרוול סופי, היא בהכרח לא אקספוננציאלית. מה שאת תקבלי בשיטה השנייה, תקבלי סטטיסטיקה של האירועים תהיה זהה לסטטיסטיקת אירועים שתקבלי אם תחתכי אינטרוול באורך T מאינטרוול אינסופי של אירועים שתקבלי מפויסון רנדום. מה שאת תקבלי, אם תבחרי מספר אחר, את יכולה להגיד שהמספר האחר הוא יתאים למספר שתקבלי מהתפלגות אחרת, מהתפלגות פויסונית
כאילו, איזה חישוב אני צריכה לעשות כדי להוכיח שזה אקספוננציאלי?
זה כבר אני אומר לך שזה לא, אינטרוול סופי זה לא...
לא, בפויסון.
מה שעשינו עכשיו, אני שואל מה הסיכוי שלא תקבלי שום איבנט, זה מבלבל, כי מה שאת אומרת זה שאת מאלצת את מספר האירועים להיות מספר מסוים. בסדר. מה זה? זה התחלה של שלדן וניוסון.
חוזרים על אותו...
כן. חשבתי חוזרים אתה ואני. זה אתה מכיר?
כן, נכון.
זה כדורסל, כן. אני אגיד לך מה...
ראיתי כל כך הרבה משחקים ב-NBA מאז שאני כזה... מה אני אגיד על זה? מה אני אגיד? אתה יודע כמה? 27 שלשות ברצף יוסטון טעה. כאילו...
החטיאה?
החטיאה. כקבוצה, אבל 27 ברצף.
סיכוי להצליח בערך שליש.
בדיוק. 27.
הסיכוי לזה?
ואני חושב שהם קונים יותר משליש בממוצע.
לא.
יוסטון.
כאילו
אתה אומר כל הזה. אבל אם תיקח שליש. 27 ברצף? מה זה?
אבל השאלה היא, אתה יודע, השאלה היא כמה אירועים, הבעיה שם זה שאתה אומר את זה בדיעבד, זה לא מראש, אתה יודע שזה
נכון.
נמשך סטטיסטיקה.
אני יכול להסתכל כמה רצפים של 27 יש בכונה. סיכוי.
לא, אבל כמה היו אירועים אחרים, היית אומר. היו... זה העניין.
אבל הטענה פה זה שכל אירוע כזה,
כל אירוע, שאני משחק 6-6, אוקיי? יצא לי 4-3, 2-1, 6-6, 5-2. מה הסיכוי שיצא לי דווקא את הרצף הזה?
אבל... טוב, אני מניח שגם כזה קל...
טוב, אני צריך לגמור להכין את החלק השני. אז אני פשוט אגיד לך איפה הגעתי, ואתה תמשיך. דיברתי על פואסון.
יכול להיות שאני אשב פה קצת בסוף כדי לראות מה...
ועכשיו הולך לעבור לדבר על המעגל RC, ו-Integrated Fire, ו-Capillary של Integrated Fire. אחרי זה נדבר על רעש.
יכול להיות שאני אשב פה בסוף.
מעניין אותך שלא רק משהו שואל את השאלה הזאת חיוך.
אני אגיד לך קטע שתדבר.
אבל האמת היא
תדירות השאלה תגדל.
כי אני מבינה
כאילו צריך לעשות על זה.
באמת? נראה לי
שנה לא, אבל כמה זמן כל החומר כבר קיים אבל...
לא, החומר כבר כתוב.
כל כתוב.
חוץ מחלק אחד ויחיד שאתה פשוט לא מצליח באמת לא עובד.
למה? כמה...
זה בשביל?
לא, החלק האחד והיחיד.
לא, החלק האחד והיחיד הזה, יש לי חלק תיאורטי וחלק של סימולציה. והחלק של הסימולציה הוא כמעט מוכן, אבל גם לא כתבתי את עליו עדיין, כאילו יש לי את הקוד, אבל לא כתבתי עליו, וגם בסוף הקוד יש לי איזה בעיה איך לעשות את זה. עכשיו אני מוסיף דברים שהגיעו
לא, זה לא קשה. זה לא קשה.
נשאר איזה 100% לשאלה הבאה.
אני מניחה שאני רוצה
אבל בגדול.
אני מאוד רוצה שיהיה סיום, אבל זה לא הולך להיות כאילו ארוך יותר משהו. לא חשבתי על זה בצורה הזה, אבל מה יצא?
לא, אבל אני חושב שזה בסדר. רגיל. אוקיי.
מה אתה רוצה, אוקיי?
אני גם. זאת אומרת, אני טוב, אולי לא. אני אמור כבר לעשות ממש.
פרקטיות?
רציתי 3 חודשים.
וואו.
כן, אבל אז פשוט נראה לי פשוט שם. למרות שהם לא יגידו שום דבר, הם לא יגידו. אבל אמרתי, כי בקורסים זה כל אחד אנשים די נעלמים. ראיתי את זה בקורסים. וכמה מתחילים שתדע. זה לא שם כאילו.
מה מתחילים את הדוקטורט?
דוקטורט 1.5 שנה, אבל עשיתי גם את המאסטר. כבר אני עובד איתם כמעט 7 שנים. אז כבר עברתי את כמה קורסים וראיתי את זה. לפעמים הם ממש בעניין וכזה משהו בחוק עכשיו הם לפעמים. לפעמים הם נעלמים. אז לא היה לנו בכל זאת הרעיוני בגלל שהיא עבודה וזה עבודה יומית. אז סגרתי חודש אחרי.
איפה?
טסתי לסיילנד, קמבודיה וישראל. כן? אבל אני אהיה כל החגים שם.
לא היה כאן.
לא הייתה.
מלא לא בטח פה. בסדר,
מי עשה? יש מקום שאין? אני קורא. כן,
וגם בקרי אני לא צפונית, אני לא...
בשביל לא להפסיד. סתם משהו. זה משנה מצחיק, ואני קצת לא ויש את המבחן הזה, לא, ויש את המבחן
רגע, אתה עבודה לך 5 חודשים?
לא, ולא יוצא כך הרבה מהעבודה, כי כל החגים יש גם עכשיו כזה c'est que les gars sont là pour faire beaucoup de liés à décisionner. Ah ouais. Comment ça marche avec ça? C'est fort difficile. Quelques cheveux, des talents, on va changer de phrase. Je sais. גר ולומדת.
non. Moi c'est pas compliqué, donc si c'est négatif, j'arrête.
כאילו, החליטה לרדת מהארץ?
היא לא מבטלת את החיים שלו, היא לא בתוכנית וזה כרגע, אבל אני מניחה שהיא בחיים שלה היא לא אוהבת להיות בארץ. אבל...
זה לא מובן מאליו.
אני לא אוהבת מי...
כן, כן, היא יכלה אולי.
זה פשוט סטטיסטית נראה לי, כאילו
פחות סביר. כנראה שצריך. אז רגע, כמה אתם עושים?
כולל surtout par rapport à ton travail,
משהו אחר בעולם? ואחרים?
די,
לא, זה משהו אחר, זה כמו טיפ.
לא, אחרים לא.
Moi, ça prend travailler dans une ville. En fait, tu t'en fous, tu peux dans ton coin là-bas, de toute façon, tu peux
אוקיי.
זה עכשיו לכאורה כזה. לא, mais je
רגע אם הגלחתי מגדלתי
genre,
גם...
כשאתה בגיל הזה. C'est une ouverture à chaque fois j'ai essayé d'aller à ce plaisir de partager la connaissance. Et la fourmi des תסתכלי שאני שואל על החלום שלי. Ouais, l'humidité, c'est pas l'humidité. Dire que t'as l'humidité, pour toi, c'est pas...
En fait, que l'humilité, c'est savoir vraiment ta
Bah oui. Non, mais c'est vrai en fait. C'est dans le chaud.
So we ended the last hour by describing experiments in which a monkey is presented with these moving dots and has to indicate whether the dots are moving up or down. And we will focus our attention on those trials in which there were no correlations. So there's no correct answer, but we don't care at the moment about the behavior of the monkey. We will not care about it. We'll just look at the activity in one neuron in an area known as MT, area that in which neurons are sensitive to visual motion. So what you see here, this raster, each line is a repetition. Each line is a repetition of this trial. But what was special here is that these trials were identical. So the monkey observed exactly the same realization of moving dots. Now, if we look at this raster, there is structure in it. So you see there's like 3 lines here, and here there's like an empty region and empty region here. So there is structure here, and this structure manifests in this histogram, denoting the firing rate as a function of time. And it's not surprising that there is a structure here, because well, the stimuli differed over time. So we expect that these neurons that are sensitive to motion will result in different activity over time. What is more interesting, however, that there is variability for the same stimuli between different trials. This is again what we discussed last time about what we discussed in the beginning today and also last week about reproducibility of experiments. And this is an example of a small region here, a raster of a small region here, in which the average activity is approximately homogeneous. But when we look at the distribution of inter-events interval, the distribution is approximately exponential. So, which indicates that the activity, now you already know that this is an indication, of course not a proof, that activity in the brain is timing of spikes in the brain are well approximated by a Poisson process. What about time zero, by the way? I mean, the fact that why aren't there too many spikes at the same in intervals that are very short? Refractory period. So there are 2 interpretations. One interpretation is the optimistic interpretation, which talks about a refractory period. The idea that a neuron, because of its biophysics, cannot spike the interval between spikes cannot be smaller than, let's say, 1 or 2, maybe 3 milliseconds. One thing that is worthwhile remembering is that if they would have found a large number of pairs of spikes with a very small interval, they would have thrown away this neuron. Because when you do spike sorting, one thing that you care about very much is the fact that you will record activity from a single neuron and not multi-unit activity from several neurons. Now, one signature of the fact that you're recording the activity from a single neuron is the fact that there are no interspike intervals that are very short, again, because of this refractory period. But thinking about it as from a scientific point of view, if this is a criterion, then clearly, if this is a criterion for excluding neurons, then clearly you will not find neurons that don't have a refractory period. It's just something to think about. So this is an example of observation, and there are other properties of a Poisson distribution, actually. In a Poisson distribution, the variance is equal to the mean. So if you look at the number of spikes in an interval, if it's a homogeneous Poisson process, then the variance should be equal to the mean. This is the data, and it is not so different from it's a reasonable approximation. We spoke about the CV, the coefficient of variation. Looking at here, the notations are different. If it's periodic, then the CV is equal to 0. If it's irregular, the CV will be positive. And the CV that is equal to 1 is the signature of a Poisson process. Now we can go to the brain and ask the question of looking at the neural activity, what's the CV? So this is an example of a study in which they just looked at the activity of a very large number of neurons in different cortical regions. So this is a supplementary motor area, this is prefrontal cortex. I don't remember what CMAR is. And they just computed the CV for different neurons. And what you see here is the distribution of CVs. And the distribution is not too different from 1. Or it's centered not too far from 1. Which is consistent with neurons whose activity is approximately Poisson-like. So taken together, this and other evidence, a Poisson process is a reasonable description of activity in the cortex. And next, we will ask the question of what are the mechanisms. And I think that some of the questions that you raised regarding basketball are actually relevant for neurons. So clearly, when you say clearly, it's never clear, but it's reasonable to assume that women giving birth in the same hospital, the timing of delivery is approximately independent. But we know about time scales of neurons and things that are going on within a neuron. So why should the timing of spikes of action potential within a neuron, why should they be uncorrelated? In the same sense of why should the timing of field goal attempts in basketball, why should they be independent? Because it's a question to consider and think about. But before that, we need more tools. To address this question, we need more tools. And the next tool that we will consider would be a model describing the spiking of individual neurons. So you all, well, those of you that took Lotem's course know about Hodgkin-Huxley and perhaps other models for the generation of action potentials. We will not go into these details and consider a much simpler model, again, a model that some of you already know, that is known as the integrated fire neuron. I guess not all of you know what's an integrated fire neuron, right? There are people who don't. Yeah, okay, so I will teach you. So on day one, we talked about neurons, and each neuron has has an inner part and an outer part. And this membrane is composed of it's a bilayer lipid membrane, but for the sake of our discussion, it's not important. And we have these channels where current can flow in and current can flow out. So thinking about the neuron in a framework of an RC circuit, let's just use a different color. So this would be this is the outer part, and this would be the inner part. If we inject current to a neuron, we can think about it we can think about it as an RC circuit that is characterized by capacitance and by resistance and battery. So there's a resistance here, but we typically we don't talk about resistance, we talk about conductance. And if there's a current that is going in, it's divided into capacitance current and I don't know how to call it, resistance current. And the capacitance current is simply C times the derivative of the membrane potential, which we will denote by M. And the IR will be equal to Vm minus the battery. We'll call it, this will be V rest, divided by the resistance, or Vm minus V rest times G. So the total current is equal to C dV dt plus G times Vm minus V rest. Why is there a V rest in the first place? Why do neurons have a resting potential? Why do they have a potential? What do these pumps do? They keep the concentrations of different ions in a non-balanced state, and because of the specific conductances that are specific to different ions, this results in a battery-like state. So rewriting these equations, rewriting these equations, we get tau dV dt is equal to minus V of t plus I of t times R, where V is defined to be the membrane potential measured relative to the rest potential, and tau is equal to RC. So R would be the total resistance, or 1 over the conductance, and C would be the total capacitance. So what is tau? What's the characteristic time for neurons?
And the difference in the current has to reflect to see a difference in the voltage.
I'm sorry?
The time that we take the neuron, if I inject some given current, how does it will take that I see some influence on the voltage?
How long will it take, approximately?
The tau of
Hours, days, minutes, seconds,
10
milliseconds. Let's say tau is 10 milliseconds, maybe? 1 millisecond, 10 milliseconds?
10 milliseconds.
Whatever. Okay. Sometimes it can be even 50, maybe 20, depending. But let's say between 5 and 50 and 20, this is something you can live with. Okay. So we agree that this tau is composed of two numbers. One is a capacitance and one is a resistance. So what determines the capacitance of the membrane? Sorry? Surface area. So the capacitance will be proportional to the surface area times the specific capacitance. What's the surface area of a neuron? This is more complicated, right? Let's just talk about the soma. What's the radius of a soma? Like small soma, I don't know, large somas. What's the range of the radius? I would say even less. I mean, you can find smaller granular cells. Granular cells in the cerebellum are very small, and some other cells can be very large. I don't know if you look at it's not less fashionable to study, but in the past, because of their size, aplysia, neurons in aplysia were very popular. System to study, and they are very large. So, what's the dependence of surface area to radius? Square, right? So neurons vary between, let's say, 16 and 10,000 square micrometers. Just think about the soma. So how come that the tau is so constant, or the tau changes by a factor of maybe 4, whereas the surface area, which determines the capacitance, varies between 10 and 10,000, 3 orders of magnitude. Resistance. So resistance is also resistance, or the conductance, G, the conductance, is also proportional to surface area. And as a result, RC is independent, approximately independent of the surface area. So the numbers for specific capacitance would be 1 microfarad per square centimeter, and specific conductance, would be something like 0.01 to 0.1 millisiemens per square centimeter. And I don't know if you know, Idan Segev argues that the specific capacitance of human neurons is different from the specific capacitance of other neurons in other animals, and this is part of what makes us human. He had a paper about a year ago arguing this. So the time scale of neurons is about 50 to 20 milliseconds. What's the time scale of an action potential? Maybe 1 millisecond, sometimes it's half a millisecond, depending. So how can you have, if the characteristic time of a neuron is, let's say, 10 milliseconds, how can you have events that are 1 millisecond long? Doesn't make sense, right? They need to be the same time scale of the neuron. No? Okay, it's not passive, so what? I'm sorry? So this is the answer. So during an action potential, the conductance substantially increases. So resistance substantially decreases. So the characteristic time of a neuron during an action potential is in fact much shorter than this time scale. Okay, so now we understand all the biology of an action potential, right? We're all happy. And even better, we have an equation that tells us how the membrane potential changes. With the input, excluding the times in which a neuron fires an action potential, and the general solution of this equation is V of t is equal to V of 0 e to the minus t over tau plus r over tau, an integral from 0 to t dt prime e to the minus t prime over tau I of t prime. So this is for this differential equation. This is general solution of this equation. So just for the sake of just to show an example, so let's say that the input looks something like this. So it is 0 for negative times, and it's equal to constant for positive times. So this would be something like this. Then the voltage as a function of time will be equal to the initial conditions, e to the minus t over tau, and if t is large, then this would be. And if we start from 0 after being for a long time at 0, then this would be equal to 0 plus r over tau, an integral from 0 to t dt prime e to the minus t prime t minus t prime over tau times I, and this is just equal to IR1 minus E to the minus E to the minus T over tau. This is for a positive T. So this kind of input, the membrane potential will look something like this. This is 0. This is T. This is 0. This is IR. And this is tau. And in the limit of T goes to infinity, we're just left. It will converge to IR. I guess all of you, most of you know it. Now the model that we're talking about is known as the integrating fire model, or the leaky integrating fire model. Basically, what it tells us that when the membrane potential is below a threshold, the dynamics are characterized by this equation. And when the membrane potential exceeds a threshold, then we have an action potential, a spike, and the membrane is reset to a resting value. So this is a membrane potential. This is the integrating fire model. So for V that is smaller than some threshold, which we often denote by theta, the dynamics is just the passive membrane dynamics. And when V reaches a threshold, then we have an action potential, and V goes to 0 or sometimes different resetting values. Questions about the model? And we will use this model as a model of neural activity, of like a simplest possible model for the generation of action potential. So again, as an exercise, what we will do now is compute the rate, the firing rate of an integrating fire model as a function of the input. So how are we going to do that? So we assume that the input is constant, and we want to compute the rate of action potential. Okay, so let's. I fully accept what your suggestion. Let's just do it slightly more slowly. So let's consider. Let's think about it in a graphical way. So let's say that this is a membrane as a function of time. Now we start from 0, from the rest state, or the rest potential, and now we inject a constant current. So the behavior of the model will be there will be an exponential, will be an increase that will exponentially converge to IR. So if IR is smaller than the threshold, the model will behave something like this. And what will be the firing rate? Well, it will never spike, never fire an action potential. On the other hand, if IR is above this threshold, then if the membrane would have been passive, then the model would have behaved this way. It would have converged, again, with a time constant tau to this new value of IR. But since the model fires an action potential whenever we reach theta, this will not happen. There will be an action potential at this point in time, and then a reset to 0, after which there will be, again, it will integrate the input until it reaches this point, firing an action potential, and so on. And in order to compute the firing rate of the neuron, what we need to do is to compute the time it takes the membrane to reach the threshold. Now, in fact, actually, this is something we've already done. We have the equation that relates time to the membrane potential. So the time for an action potential will be the time in which theta is equal to IR 1 minus e to the minus, let's call it T0 or something, to denote this is the time of the TS, time of the spike. So the time to fire an action potential is the time such that IR times 1 minus e to the minus TS over tau is equal to the threshold. And just solving it, this results in tau s being equal to minus tau log of 1 minus theta over IR. And if we want to compute the firing rate would be equal to 1 over Ts. And if you are religious about it and you want, we discussed the refractory period. So sometimes we will be interested in incorporating a refractory period. Then this is a way in which people often incorporate the refractory period in this model. איזה סימן? ני? Firing rate. Let's call it R. Yeah, let's call it R. We used R throughout the course, so let's use R. We don't have other R's here, right? We have resistance, but it's capital R.
Your R looks a lot like your B.
R. Okay. Use Hebrew to clarify. Okay. So now we have the necessary tools to think about the generation of action potential. And I'd like to remind you that we are interested in understanding the Poisson-like behavior of cortical neurons. So we already know that this Poisson-like activity is likely to be a network phenomenon, and this is because I showed you that individual neurons in vitro are rather regular. So it should have something to do, this weird activity of the neurons should have something to do with the input that they receive. Now, what kind of input cortical neurons receive? Input from other cortical neurons. So other cortical neurons are Poisson. We know this from experiments, from the recordings. So we need to understand how a model, well, we want to understand how neurons respond to this Poisson-like input that they receive from all other neurons in the network. And to address it, what we will do is try and understand how this integrated fire model responds to the rather stochastic input, or to this noisy input in the network. So this is our goal. And again, as we did in today and in the last several classes, we will need tools. We will need new tools in order to understand, or in order to characterize the response of the integrated fire to this noisy input coming from the network. So this is what we will do now. We will talk about something that is known as white noise. So our goal so we have our neuron, still have it here. And before being formal about it, what we want is to understand how this neuron would respond to something that looks like this. Something nice, it's regular. So let's say that this is the input to the neuron, noisy input. So how are we going to, so in order to study how a neuron responds to this ugly thing, we need to characterize this ugly thing. Now I think that you all appreciate the fact that we see these ugly things all over the place. I don't know, if you measure EG, okay, you see things horrible. So we need to characterize it somehow, mathematically. So this thing is characterized by three, has three properties. First, it has a mean. Right? It has a mean. Now, when I talk about a mean, I can talk about two things. I can talk about mean over time, and I can talk about mean over realizations. So let's say I'm doing a recording today, tomorrow, the day after tomorrow, until I die or graduate, whatever comes first. Okay, so this would be, so I'm talking about here about average about realizations. So until I die. Okay, that's one thing. And a second thing that characterizes this ugly thing is the variance. So the variance, delta I, is equal to I minus average I. So delta I is a measure of the height of this thing. That's a second measure of this ugly creature. A third thing that characterizes it is the time scale, or the correlation time. So if I take this square and I zoom, this is what I see. right? This is zooming on this square. And there is a characteristic time here. We'll call it tau correlation. So this noisy construct is characterized, I think, by, as I said, by three things: the height, the mean, and the correlation time. And just let's talk about the correlation time now. So what's the correlation function? Let's talk about the correlation function, the idea of a correlation function. So for the sake of simplicity, let's assume that the mean is 0. We already know how to deal with non-zero mean. So let's consider now I of t that looks like this. Okay, you got the idea. So this is time. We'll call this is tau correlation. And the idea here is that we have a signal that is randomly drawn every tau correlation. So